So in this video, I want to say a bit more about topological manifolds, and I want to say something about charts. So if we let M be a topological manifold, then a coordinate chart, or just a chart on M, is a pair U, phi, where U is an open subset of M, and phi from U to V, where let's take V to be the image of U, is a homeomorphism where V, which is the image of U, is open in Rn. And by the definition of a topological manifold, every point in the manifold is in the domain of some chart. So we can say for every P in M, there is a chart U, phi, such that P is in U. This is the locally Euclidean of dimension n condition in the definition of a manifold. And we often call U the coordinate domain or coordinate neighborhood, and phi is called the local coordinate map. And if in coordinates phi of P is given by x1 of P up to xn of P, where x1 up to xn are the component functions of the map phi, these are called local coordinates on U. And as is often the convention in differential geometry, we use superscripts instead of subscripts for the x1 up to xn. Okay, so let's look at some more examples of topological manifolds. So let's first take graphs of continuous functions. So if we let U be open in Rn, and if we let F from U to Rk be continuous, then the graph of F, which we denote by gamma of F, is defined to be the set of pairs xy in Rn cross Rk, where x is in U and y is equal to f of x. So this is the graph of x. This has the subspace topology because it's a subspace of Rn plus k. And if we let pi be the projection to the first factor, so if we let pi from Rn cross Rk to Rn be projection to the first factor, and if we let phi be pi restricted to the graph of f, then phi, well, we have in local coordinates phi of xy is equal to x for every xy in the graph of f. And we can also say that, phi is going to be a homeomorphism. So it's a nice exercise, actually, to check that phi is a homeomorphism. So why is it a homeomorphism? Well, that's for you to think about, but certainly it's continuous. It's the restriction of a continuous map. We can explicitly write down an inverse. In fact, I'll tell you, and you can check that the inverse is given by this. And so to prove it's a homeomorphism, you also need to prove that the inverse is continuous. So certainly this map phi is a homeomorphism and is in fact a global coordinate chart. So we can say that the graph of f with phi is what's called a global coordinate chart. It's a global chart because we only need a single chart to cover the entire manifold. For every point of the graph, this function phi is a homeomorphism to an open subset of Rn. So certainly it's locally Euclidean of dimension n, and we also have, because the graph is a subspace of Rn plus k, it's second countable and Hausdorff. So therefore, the graph of f is a topological n manifold. Okay. So now let's look at a second example. Let's look at the n-sphere. So how is the n-sphere defined? Well, Sn is in coordinates given by x1 up to xn plus 1, where the sum of the squares of the xi is 1. So this is just a set of points in Rn plus 1, a unit distance from the origin. So this is contained in Rn plus 1. So again, it's a subspace. It has the subspace topology, which means it's automatically second countable and Hausdorff because Rn plus 1 is. So all we need to do is to prove that Sn is locally Euclidean to prove that it's a manifold. So how we'll do that is, again, by constructing explicitly coordinate charts that cover Sn. So for each I, for each positive integer I from 1 up to n plus 1, if we denote by ui plus the set of points in Rn plus 1 where xi is positive, and if we denote by ui minus the set of points in Rn plus 1 where xi is negative. And then what we've got is these ui plus and ui minus will cover all of Sn, and every point of Sn will lie in at least one of these ui plus or ui minus, because there's no point of Sn where every coordinate is 0. So therefore, every point has at least one coordinate that's either positive or negative. So every point lies in at least one of these sets. So, and if we then let f from the n ball to the real numbers be the function f of u is root 1 minus the length of u squared, then what we want to do is to show that ui plus intersect the sphere and ui minus intersect the sphere are both graphs of continuous functions. So this function f is continuous, you can check that, and we can also see that if we were to work out f of x1 up to xn plus 1 where we omit xi, sorry, I should have a superscript here, and a superscript here. So the hat denotes that we're omitting fi, and if we work out f of this would be the root of 1 minus the sum of j not equal to I, xj squared. If we work out this, we know that the equation of the sphere, we need that the sum of the xi squared is equal to 1. So we know that this sum here is 1 minus xi squared. So this is the root of xi squared, which if xi is positive, this should be a superscript again. This is xi squared like this, and xi squared like this. So this is the modulus of xi. So if xi is positive, this is equal to xi. So we can say that ui plus intersect Sn is the graph of xi is equal to f of x1 up to xn plus 1 with, with xi omitted. And that's because on ui plus we're taking the xi is positive, so we can take the positive square root. And likewise, ui minus intersect Sn is the graph of xi is equal to minus f of x1 up to xn plus 1. Again, with xi omitted. So, each subset, ui plus minus intersect Sn, is the graph of a function, and therefore, by the previous example, is locally Euclidean of dimension n. And therefore, because these ui plus minus intersect Sn cover Sn, as we mentioned earlier, every point is in one of these sets, in one of these coordinate domains, we must have that the set of the ui plus minus intersect Sn, and also phi I plus minus, where the phi I plus minus are given by phi I plus minus of x1 up to xn plus 1 is x1 up to xn plus 1, just with xi omitted. These are charts. So these are coordinate charts for the n-sphere, and therefore Sn is an n-manifold. And maybe just to finish this off, I'll just draw a sort of quick picture to explain what's going on. So if we imagine the two-sphere, then the top half of the two-sphere, not including the equator, so just this sort of top half of this two-sphere, if our coordinates are x1, x2, x3, then this top half would be where x3 is positive, so this would be u3 plus. And then the bottom half down here would be u3 minus. And then if we were to take, we could divide it differently. We could take in red, we could take the sort of this half over here. So this would be where x2 is positive. So in red, this would be u2 plus, and the other side over here would be u2 minus. And then we could also divide it differently. We could take the front half, the half closest to you, looking at this, the projection of this sphere onto the screen, that would be u1 plus, and the back half would be u1 minus. And we can see every point of the sphere lies in one of those 6 coordinate domains. So visually that's what's going on. So that's a proof that Sn is an n-manifold.